Hey guys, this is Coach Dennis here. I'm going to go over our periodic table notes for today. And one thing to keep in mind from here on out, every day in class, what you should be doing is pulling up a periodic table. So what I have up here is ptable.com. If you search periodic table, this will probably be the first thing that pops up when you do that. So always want to have a periodic table up every day, whenever you're doing any assignment here in chemistry from here on out, because you're more than likely going to need to use it. So just keep that in mind. So here I have our notes. I put them in a PDF form just so I could have my periodic table to the side along with my slides, because if you try to do it on PowerPoint in presentation mode, it won't let you. So, and if you want to know how to turn a PowerPoint into a PDF, I can show you guys how to do that too. Just email me. I'll make a quick video about it. And if you guys just email me and just want a video over anything really, I can make one for you within that day, hopefully. So let's talk about the periodic table a little bit. This is going to be the most important thing that you learn throughout the year, because this is how you're going to be able to do everything in this class. So if you don't understand how the periodic table works and you don't understand what these different numbers mean, then it's going to be a rough go for you. So make sure that we're trying these out and trying to understand the periodic table, because the class gets more and more difficult as the year goes on, but it's not going to be as difficult as long as you are understanding the periodic table. So let's go over our learning target. So I know the basic arrangement of the periodic table, symbols, group, and types of elements. So let's go through all that. So first, what is an element? So an element is matter that's made up of one type of atom. So remember how we know what atom is which atom is by the number of protons, which that is given by our atomic number found at the top of our tiles on our periodic table. So depending on what element I want, if I want to know how many protons it has, which indicates what element it is, that number is going to be at the top, our atomic number. So element is a specific type of atom. Periodic table is how we organize those specific atoms, and then knowing the symbols. So if you look, there are symbols. Sometimes they're one letter, sometimes there's two letters, but what you'll always notice is the second letter is lowercase. And this is important once we start going to formulas and really getting into chemistry, because the difference between a capital letter and a lowercase can be literally life and death. So I'll give you an example real quick. So here I have a C, capital O. This is what we call carbon monoxide. You guys have probably heard of it before. You probably have a detector in your house. What carbon monoxide is a gas that's given off whenever we combust anything, basically put anything on fire. And this gas, what makes it so dangerous is it doesn't have a smell, and when you get poisoned by it, you just slowly get tired and fall asleep. So carbon monoxide is not good to breathe in, can cause death, so not good stuff. Well, whereas if I have C lowercase o, that's where we have cobalt. So found on our periodic table, it's number 27, cobalt. I mean, if you have too much cobalt in your blood, you can get what's called cobalt poisoning, but the way for that to happen is very rare. Actually, it can happen. Old hip transplants used to use cobalt, and if those break, it would leach into the body and cause people to get cobalt poisoning, actually. And that's the only real known cause of that, but that's just a little FYI information. But yeah, these are two separate things. Cobalt's a metal that can be used for a lot of purposes, usually not that dangerous. Carbon monoxide, this can kill you if you breathe it in. So that's the difference between a capital O and a lowercase o. So make sure we're doing our symbols correctly. Next up, we have compounds, which is where we have two or more elements linked together, or what we call a bond. And we'll get to bonding next unit. So, oops. No, bond, whatever. So yeah, bond is what that is. So in the case of like water, H2O, No, I don't want to move you. So H2O. We have 2 hydrogens for every 1 oxygen. So we have 2 or more elements within this compound. So in the case, hydrogen and oxygen. And this 2 is telling me that I have 2 hydrogens. So if we draw that out, and we'll learn how to draw these a little bit, what we call Lewis structures. Oh, that's not what I wanted. No, stop it. Yeah. No. Why does this keep doing this? So here we have our water molecule. So we have 1 oxygen, 2 hydrogens to make it. I'll do another compound. So C6H12. And you guys may have seen this last year in biology. Yeah. The H's, they don't like to be drawn out too well. All right. H12O6. So here we have 6 carbons. Sorry, that's supposed to be a 6. 12 hydrogens and 6 oxygens. So the number down to the bottom, the subscript, that'll tell us how many atoms are within that compound. And we'll start going more through compounds next unit, specifically ionic compounds. Next, we'll talk about our scientists who came up with the periodic table. We really don't talk about a ton of scientists this year, but this is one you do have to know, is Mendeleev. He's the one who actually started to organize our elements that were known and started arranging them in a logical way. So what he did was he found all the different properties of all of the elements that were known at the time, which weren't that many. It was like 30 something. This is kind of like what his original periodic table looked like. There wasn't a lot of them. But what he did was he started putting them in groups or columns of things with similar properties. So if you notice, like our periodic table, you have lithium, sodium, potassium, stuff like that. Things that have very common properties. He started to put in groups or columns. And then eventually he started putting them in rows, also along with the columns. And he noticed there's periodicity to it. So you would, start and end, and then there's an obvious start and end again. So that's why we call it the periodic table. The one thing that his periodic table, there's been quite a few changes to it, but the biggest change is that he originally organized his by atomic mass, which is mostly correct, but there's a few examples where it's not, like in the case of tellurium, and iodine. So if you look, tellurium is 127 atomic mass units, almost 128, whereas iodine's 126, closer to 127. So if we're going by mass, these would be out of order. So there's only a couple examples of that. So he was mostly correct with his periodic table. It was just that, he didn't have the technology to know how many protons there were in it, and that's what we go by now. So the atomic number or the number of protons. So here's an example of what his original periodic table looked like. It's changed, quite a bit, but one thing you'll notice is that there's these spaces here. So what made his periodic table and people feel like they feel that it was correct was once more and more elements started being discovered, they started fitting in the spots that Mendeleev said they would. So then people were like, maybe this guy knows what he's talking about, once they started discovering more and more elements. Now we've discovered or made all of them, which is 118 total. But generally, the last ones, they are made in a lab, and they're very unstable, so they don't last very long, and you can't make a lot of it if it does. So, but yeah, he organized the table. He put in blank spots. Eventually, those blank spots got filled by elements that were found. So that kind of gave substance to his periodic table. And now we use it all the time. Well, use it for everything in chemistry. So yeah, modern periodic table we go by atomic number. Remember, this is equal to our number of protons, which gives us number of protons, which gives us our identity of our atoms. So it goes by that. So our columns are what we call groups, or you'll hear them called families sometimes. The reason why is because they act similar and they do a lot of the same things. And then we have periods. Sometimes I will call these energy levels. And that'll make sense once we get to valence electrons. But I won't go over that now. So here, example of our periodic table. If you notice, these aren't any element names and there's blank spots. This means this periodic table is probably 10, 15 years old just by what's been discovered or not. So we have our different groups. So group 1 is our alkali metals, which is very reactive metals. Generally, you're not going to see these, like, you can't just mine these out of the ground because they're so reactive, they're going to react with something just within the air. So those are our alkali metals. Our alkaline earth metals are metals that are still really reactive, but not quite as reactive as our alkali metals. Groups 3 through 12, that's what we call our transition metals. These are generally what we think of as metals, like your copper, silver, gold, iron, so just what you think of, titanium, that stuff. Then we have our halogens, which is group 17. These are our nonmetals, and they're very reactive nonmetals. And then finally, our noble gases, which are non-reactive gases. And the reason they're non-reactive goes back to valence electrons, and we'll go over that here in a class or two. So I only got a few minutes left before my 15 minutes are up, so I might do these really quick. And you can always just look at these because not really too in-depth. So first we have metals. So metals, and you don't really see the stair step here, but it will tell you what type of elements they are in this table. But our stair step, it usually runs, see where boron is? Oops. It's kind of hard to see. So boron, it runs right around here. So everything to the left, everything to the left of our stair step. All right, come on. So everything to the left of our stair step. I did pop that up. Is going to be our metal. So they have luster. That means they're shiny. They're solid at room temperature, good conductors, malleable, so that means I can shape them, and ductile, which means I can draw it in wire. Our nonmetals are to the right of the stair step, so our stair step would be here, so everything to the right, found right there. So it's basically the opposite of metals. So whatever metals are, our nonmetals are the opposite of that. So they're brittle, they're dull, they're not shiny, not very good conductors. So if you know what the metals are for their properties, then you'll know the opposite of that is your nonmetals, and it's to the right of your stair step, which stair step is generally right here. And then finally, we're on to our metalloids. So our metalloids are colored on this periodic table as this like forest green right here, or I don't know what you'd call this. I'm not a colorist. But it's boron, silicon, germanium, arsenic, antimony, tellurium, and acetine. These are all of our metalloids. These have properties of both metals and nonmetals. So they're, like the best example I can give is silicon, which is a metalloid that has both properties. So it can conduct electricity, but doesn't heat up as much as a metal, so that's why we use it in computer chips. And then here you see them on our table. One thing to note is that we have one nonmetal to the left of our stair step, which is hydrogen. Now I've only got about 10 seconds left before this video's up, but here's our metals, metalloids, nonmetals right here. Make sure we know how to read this table, and have a good day, guys.